Good morning, students. Last class discuss about the slip. What are the effects of slip on different parameters? That is rotor frequency, rotor current, rotor power factor, rotor induced EMF, and then torque equation, and also torque slip characteristics. Torque slip characteristics. Now we go for the next topic. Last topic of fourth unit, that is losses. Losses in a induction motor. Generally, losses is nothing but iron losses, copper losses, and then rotational losses, friction and windage losses. Whereas transformer, friction and windage are absent because it is a static machine. But coming to the induction motor is also again rotating machine. That's why here also that losses are available. So first go for the major losses in the induction motor are stator losses. In stator, again stator copper loss, stator iron loss. The losses which are occur, so before going to this one, generally already discussed in the, why the losses will be occurring is nothing but any machine will be running continuously, and each part of that particular equipment may heat it. Because of that heat, some power is wasted on every part of the motor. So that waste of power is nothing but losses. The losses also represented in watts or kilowatts, right? So first go for the stator losses. The losses which occur in the stator of an induction motor are called stator losses. Losses which are occur in the stator winding, that losses are called stator losses. So again, the stator losses may be classified into two types: stator copper losses and stator iron losses. As usual, copper loss is nothing but proportional to the square of the current. So here stator is nothing but I, we are represent I1, rotor 2, I2. Stator current is nothing but I1, rotor current is nothing but I2. So we have to differentiate with a numbers 1, 2. Now stator copper loss is nothing but I1 square R1 per phase values. Iron loss is nothing but, so always constant, that losses are also hysteresis and eddy current losses. So now rotor losses, which these losses are occurring in the rotor of an induction motor are called rotor losses. Rotor losses are maybe a rotor copper losses or rotor iron losses. Copper loss is nothing but rotor I2 square R2 per phase. Iron loss is nothing but, since under normal running condition, rotor frequency is very small. Therefore, these losses are very small and it may be neglected. Stator copper loss are there, stator iron losses are there, but coming to the rotor copper loss are available, but rotor iron loss are neglected. Then mechanical losses. The sum of windage and friction losses is called mechanical losses. Mechanical loss is nothing but windage, and sum of windage and friction losses is also called as mechanical losses and rotational losses. Now, how to explain the power flow diagram. Input power is the electrical power for three-phase induction motor. Output power at the shaft is a mechanical power. And in between these two, the electrical power is given to the stator. That means in the stator copper loss are available, stator iron loss are also available, right? So input power is given to the stator. In the stator, what are the losses are occurring? Stator copper losses, stator iron losses. So these two will be included in the stator. Now the stator output is nothing but rotor input. In the rotor again, rotor copper losses. There is no rotor iron losses. Why? Because it is been neglected. Rotor copper losses, then mechanical losses, and also that means these two losses are included in the rotor. Two losses are included in the stator copper loss and stator iron loss, and two losses are included in the rotor, that is rotor copper loss and mechanical losses. So now some mechanical power is developed in the rotor. That means electrical power is converted into mechanical power. So under that process, four losses are included: stator copper loss, stator iron loss, rotor copper loss, mechanical loss. Now from this power flow diagram, you have to determine the efficiency. Efficiency is equal to output power by input power, otherwise rotor output by stator input. So output by, generally motor is nothing but we know the input. We know the input. We don't know the output. Therefore, output is equal to input minus stator copper loss, stator iron loss, minus stator copper loss, minus stator iron loss, minus rotor copper loss, minus mechanical losses. That means input minus losses by input is nothing but efficiency of a given three-phase induction motor. And also from this power flow diagram, you can easily determine the mechanical power developed and also stator output, that is nothing but rotor input, electrical input, and also we have to predetermine the efficiency. That means we have to calculate the individual losses. Look at the picture clearly. Look at the picture clearly. So now next we go for the important relation. This is also very important. Relation between the rotor copper loss, slip, rotor input. So generally we have to given the power to the three-phase induction motor is nothing but three-phase electrical power. That may be converted into mechanical power. So electrical power is converted into mechanical power. Therefore, first we have to determine the mechanical power developed in the rotor. So mechanical power developed in the rotor is nothing but, so I square R power. So I2 square R2. So 1 minus S by S. Then rotor copper loss is nothing but I2 square R2. From the power flow diagram, look at the figure. Rotor output is equal to mechanical power developed plus rotor copper losses, right? So rotor input is equal to mechanical power developed plus rotor copper losses. So mechanical power developed, that is this one, I2 square R2 1 minus S by S plus rotor copper losses I2 square R2. So that is equal to, you have to take the common factor of I2 square R2. 1 minus S plus S by S, that is 1 by S. Therefore, rotor input is equal to I2 square R2 by S. I2 square R2 by S. Now from equation 1 and equation 2, we get rotor copper loss by mechanical power developed is equal to rotor copper loss I2 square R2 divided by mechanical power developed, that is I2 square R2 into 1 minus S by S. Here I2 square cancel to each other, R2 also cancel to each other. Therefore rotor copper loss is equal to rotor copper loss is equal to S by 1 minus S into mechanical power developed. Rotor copper loss is equal to S by 1 minus S into mechanical power developed. So from equation, again from equation 1 and 2 we get rotor copper loss by rotor input, that is equal to I2 square R2 by I2 square R2 by S. Therefore, I2 square cancel, R2 cancel. That means only rotor copper loss by rotor input is equal to S. That means rotor copper loss is equal to slip times of the rotor input. Rotor copper loss is equal to slip times of the rotor input. Therefore, we have to derive the relation between the rotor input, rotor copper loss, rotor mechanical power developed. That is equal to 1 is to S is to 1 minus S. So P2 is to PCU is to P mechanical is equal to 1 is to S is to 1 minus S. Very important. So now determine the efficiency. The ratio of output power, that is mechanical power developed, to the rotor input is called rotor efficiency. Rotor efficiency is equal to mechanical power developed by rotor input. That is mechanical power developed is nothing but I2 square R2 1 minus S by S divided by I2 square R2 by S. So SS cancelled, I2 square R2 square is also cancelled, I2 square R2 is also cancelled. Therefore, rotor efficiency is equal to 1 minus slip times, that is 1 minus S. Rotor efficiency is equal to 1 minus S, right? So far discuss about the different types of losses occurred in the three-phase induction motor, relation between the rotor input, rotor copper loss, mechanical power developed, that is equal to 1 is to S is to 1 minus S. Then rotor efficiency, that is also equal to 1 minus S, that is 1 minus slip times, right? Now this in this unit totally three-phase induction motor is a AC type of motor. This type of motor may be utilized widely in industrial areas or residential purpose, or it may be a laboratory purpose, that is workshops, all these things. Why this three-phase induction motor is widely used in industries? That is more than 80% of industries may prefer the three-phase induction motor because of it is having so many advantages. First one, the machinery is robust and simple construction, and it is having less maintenance cost. And it is having good power factor and reliability, and it will be providing high efficiency, so little maintenance cost. So all these advantages, the three-phase induction motor is put into the high. That means widely used motor is nothing but three-phase induction motor. And it may be utilized in so many applications, that is cranes, hosts, elevators, washing machines, and also textile mills, gas extracting mills. All these are the applications of three-phase induction motor. Now, what is the construction? Construction is nothing but having stator and rotor. Rotor again classified into squirrel cage and slip ring induction motors. Right. Stator is nothing but stationary part and rotor is nothing but rotating part. And difference between these two, very very important. Next one is principle of operation. Whenever a three-phase AC supply is given to the stator winding, so it may develop the alternating flux, that is rotating magnetic flux. That rotating magnetic field, that is RMF, is rotating with synchronous speed, it is 1500 rpm empirically, and it is ns is equal to 120 f by p rp. Numerically, that is 1500 rpm. Once the rotating magnetic field rotating with synchronous speed, and it will be uniformly distributed throughout the machine. So this rotating magnetic field will touches the rotor conductors when rotor conductors are short circuit only. Then the rotor conductors cut the magnetic flux coming from the stator. Then so an induced EMF will be induced in the conductors. Because of that induced EMF, some current will flowing on the rotor. So now that rotor then acting as a current carrying conductor. That means some force acting on the rotor conductors. Because of that force, twisting moment of force or turning moment of force is nothing but torque. This torque will gives motor rotate the with some speed and some direction. Now rotor three-phase induction motor may rotating with a speed of 1300 or 1400 or 1200 or 900 or more than 1500, but not 1500. It is rotating with below rated speed or below synchronous speed or above synchronous speed, but not at synchronous speed. Suppose it is ready to reach the synchronous speed, at that time the relative motion between the stator and rotor must be zero. That's why again after some time again it will be rebuild the magnetic flux, rotating magnetic flux, and again it will be produce the, that may lead to produce the rotating torque that moves the motor. What is the thing here? Three-phase induction motor is a self-starting motor, and it is not running with synchronous speed. It may running with below or above synchronous speed. That's why the rotor, the three-phase induction motor is a asynchronous motor, right? Production of rotating magnetic. How much of magnetic field is produced in different situations? That is omega t equal to 0, omega t equal to 60 degrees, omega t equal to 120, omega t equal to 180. At any time of instant, the magnitude of magnetic RMF is same. That is 3 by 2 pi m. That is 1.5 pi m. 1.5 pi m. Right? By using vector diagrams, you can derive it easily at every instant of time. So next go to the torque equation. The torque is directly proportional to the rotor flux, rotor current, rotor power factor. Flux is directly proportional to the EMF, that is E2R, and rotor current is nothing but I is equal to E2R by Z2R. Power factor is nothing but R by Z, that is equal to R2 by square root of R2 square plus SX2 square. So now combine all these things and leave the proportionality. P is equal to K by 2 pi ns, or three phase 3 by 2 pi ns S E2 square by R2 square plus SX2 square. Suppose you are getting the condition for maximum efficiency, for maximum torque, you are getting a condition R2 is equal to SX2. Put that value in full load torque equation, you are getting the maximum torque equation, that is T is equal to 3 by 2 pi ns E2 by 2x2. So maximum torque does not depending upon the rotor resistance, but starting torque will depending upon the rotor resistance. That's why the slip ring induction motor having more starting torque compared to the spiral induction motor. Then slip. Slip is nothing but difference between stator speed and rotor speed, and it is expressed as stator speed. Slip speed is nothing but difference between the stator and rotor speed. So like that you have to, and that slip may be affect on the different parameters. Rotor frequency Fr is equal to Sf, rotor induced EMF E2R is equal to S into ER, and current is equal to I is equal to V2R by Z. So now problem will be coming from this unit, that is slip on different parameters, effect of slip on different parameters and torque equation. Right? We discuss about the next class. Problems will be discussed in the next class. Right? Thank you one and all. So in this unit, main important questions are principle of operation, construction, torque equation, torque slip characteristics, and relation between the input, copper loss and output. These 5 questions are very important. Thank you one and all. To see this video, please subscribe TBS Talk.